Hello, my name is Alexander Prashala, and today I'm going to be discussing in depth my circuit design and analysis project for MEMS0031 with Dr. Berry. I decided to base my project off of one of my favorite television series of all time, Neon Genesis Evangelion. As a synopsis for this task, we were tasked to design a circuit with the following components: our breadboard, our LEDs, our potentiometers, our single-pole double-throw switches, battery snaps with ends already soldered, supercapacitors and/or our inductors, and our resistor. As an overview of my choice of design for this project, like I said before, this is based on my favorite television series, or one of them of all time, Neon Genesis Evangelion. A overview of the concept of the show is that in the near future, Earth is being attacked by an ancestral race of aliens called angels, and these angels are attacking humanity, and the only way we can defend ourselves against them is with these supercharged, superpowered cyborg units called Evangelion units, EVAs for short. They are part machine and part living organism, and they are piloted electronically from within by children inserted into a capsule within their spine. We will be modeling in this project the Evangelion's three power sources. The primary source is, we're going to label it number one, is the presence of an umbilical cable. You can see in the image here, Unit 2 has in its back its umbilical cable, and this is the Evangelion's primary power source during battle with these monsters called angels. It is a direct feed of power from an external source connected to the Evangelion unit by this tether. The secondary power source is auxiliary power, which is battery backup storage within the Evangelion unit itself. If the umbilical cable gets severed during combat with an angel, as does happen often because the combat with angels is often destructive, the internal battery backup power system keeps the Evangelions going for a finite amount of time, even though their umbilical cord is cut. In the show, this is 5 minutes long. Finally, if all else fails and the Evangelion's tether has been severed and the auxiliary backup power battery packs are completely expended, and the EVA and its pilot are in grave danger, the EVA, because it is a majority biological, it can take on a mind of its own with a surge of biological finite energy called Berserk mode. In this mode, the behavior of the Evangelion is erratic and unpredictable, and the pilot has no control. As we have outlined the Evangelion's three primary power sources, we will analyze the circuit on the right, which I have constructed to model this behavior, in three time frames: steady state, auxiliary power usage, and berserk mode, in that order. For specifications, I have set R1, R2, R3, and R4 all equal to 1.5 ohms to represent current being drawn into the capacitors in order to fuel both the berserk mode and the auxiliary power. Rm, resistance modular or resistance mechanics, is representative of the Evangelion's power dissipation functions within itself, as the Evangelion has many things that need to be powered for it to work properly. That is obviously set to 4.7 ohms, which is higher than the other ones to represent this much greater dissipation of power. We have 0.1 farads as C1 and 0.1 farads as C2 because that is what the model that we were given, the maximum capacitance that we were given. And our battery, our source voltage, was measured to be 1.342 volts, even though it says on the battery pack that it is 1.5 volt. Firstly, we are going to analyze the time frame of which our circuit is at steady state. T is less than 0. We will apply node voltage analysis at node A, which results in the equation our source voltage minus VA over 1.5 ohms is equal to VA minus 0 volts, as it is ground, over 4.7 ohms. We know our source voltage is equal to 1.342 volts, and after solving for one equation, one unknown setup, MATLAB is not needed, and we find our VA to be 1.017 volts. We now know that the voltage between node A and ground is our initial voltage at both capacitors C1 and C2, as the diagram shows. So, VO of our C1 for time less than 0 is 1.017 volts, as is VO for C2. In combat with the angel, the umbilical cord was severed. We now will switch to auxiliary power by flipping the switches shown in green, both labeled 1, for our first switch of power. We are going to analyze a time frame from 0 if t is equal to or greater than 0 seconds, and t is less than 10 seconds. We know that the formula for the voltage response of a capacitor is given as follows. Vc of t is equal to VOC plus initial voltage plus VOC, all times the quantity E to the minus t over tau, with tau defined as the product of our resistance times our capacitance. We have no open source voltage at t is greater than or equal to 0, so VOC in this case would be 0 volts, and thus we are left with Vc of t is equal to VOE t minus t over tau. Tau in this case is 0.1 farads times 1.5 plus 4.7 ohms, which is 6.2 ohms, so we can solve for tau as 0.62 seconds. We know that our initial voltage at time is less than 0 is 1.017 volts, as we solved for in our last slide, and because we are dealing with C1, we know that this holds. Therefore, our Vc of t is equal to our initial voltage times e to the power of minus t per tau equals 1.017 e to the power of minus t over 0.62. Continuing with the analysis of step 2, we repeat the expression that we derived in the last slide, and now because we know that R1 and Rm are in series configuration as resistors, we can use the principle of voltage division to determine V of R, Vrm of t. This being 4.7 ohms per 6.2 ohms, as Rm is 4.7 ohms, and the equivalent resistance is 6.2 ohms, times our expression for Vc of t as 1.017 e to the minus t per 0.62 volts. We will now run the circuit with the first capacitor discharging, this is the auxiliary power source, for 10 seconds to simulate the 5 minutes in the show. We get a value of 7.626 times 10 to the minus 8 volts at time equals 10 seconds. Therefore, we have a drop of approximately 1.017, the entirety of the voltage across our Rm, which is all dissipated into power. Essentially, this is 0, and the Evangelion unit has no more power to keep power from the auxiliary source has run dry. The EVA and its pilot are in grave danger. Both the umbilical cord has been severed and the auxiliary power has been expended. Now, the unit will enter berserk mode. We are going to analyze the circuit from time greater than or equal to 10 seconds. Because the values of our capacitor and resistor, due to simplicity and availability of parts, it's the same as the left side. C1 stored energy has all been expended in the form of voltage, and so after the switch is flipped, where you see the green arrow labeled 2, indicating the second transfer of power, it's been resting in an open circuit configuration ever since time started at 0 and the umbilical cord was severed. The EVA gets the same voltage and thus the same power boost for the same time as the auxiliary power if it were to enter berserk mode. After this is expended, the EVA is a sitting duck. Our expression for the voltage across our Rm, our resistance for our mechanics in our EVA circuit, at time equals 20 seconds is only slightly different. As you can see in the exponent, in the numerator of the exponent for the number e, t has added a minus 10 seconds to indicate that 10 seconds have already passed. However, their function and the output voltage across Rm is the same for the reasons stated above. Therefore, 7.626 times 10 to the minus 8 volts will be the voltage across the resistor Rm at time equals 20 seconds. After this, the EVA is a sitting duck. Okay, so I just got burned with touching one of the resistors, so let's get on with this. We have our circuit right here, and set up next to it is our multimeter. We're going to turn it on and set to voltage. Now, this circuit has been resting at steady state for a little bit now, so let this go down. We're going to measure our cross 4.7 ohm resistor voltage. And we're getting a reading close to what we should be getting, seeing as the maximum measured voltage from our source was 1.3, so it should be about half that, so it fluctuates. Here we go. About right. So what we're going to do now is flip from 1 to 2. Wait 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And see our voltage dropping rapidly to 0. Now we're going to flip it to get that. 1, 2, 3, 4, 5. Yep, and it's dropped. Yep, already to 0. And therefore it works. One additional caveat that I'd like to bring up is the idea and the evidence all here on the circuit that the LEDs were supposed to light up, 1 for 3 for when it's charging, when the power cord is on, 1 for when the auxiliary power is powered, and 2 for when the berserk mode goes on. But the resistances I used were too low in order to get a proper reading from our inductors, so I sacrificed the ability to light up the lights for the inductors.